Okay, so in a moment we'll have the final talk of this session by Dominik Geißler, speaking about probabilistic programming, meeting automata theory with exact inference using weighted automata. And once again, if you don't have your poster up yet, please do so during the break. So following this, we'll have about a half-hour break, and then we'll be back. Any announcements about how the afternoon will work?
Could also just remember, if you didn't in the morning, to RSVP for the basis event. The link is on the LAFI website at the bottom of the description.
There's still space as far as you know.
And as far as I know, there's still space, yeah.
Familiar with them as a generalized version of the well-known finite automata. Furthermore, we provide a framework which allows for manipulation of these weighted automata in such a way that the underlying probability distribution will be modified such that the semantics of the program statement affects the distribution. Again, we will see an example later on. And we do this by using very basic automata-theoretic operations such as the sequential composition of automata or intersection. And lastly, I won't talk about this today. If you're interested, you can, of course, ask afterwards or come through my poster over there. But we also proved the soundness with respect to pre-existing operational semantics as introduced here. OK, first I would like to introduce the model. So you are all on the same, or we are all on the same page. First, the general idea is we want to model these probability distributions as weighted automata, and therefore our program semantics transforms these weighted automata in such a way that the effects are modeled as these basic automata-theoretic operations. So here we have a simple weighted automaton. We can already see the difference between weighted automata and the more generally known finite automata. We, for instance, have this 1/2 here, right? So we have weights attached to initial and final states. Here, if I omit a weight, this just means the weight is equal to 1. And we also have this 1/2 x here, which is also something we would not be able to see very often. So how do we now evaluate these weighted automata, or what do they mean? Well, you can think of these weighted automata generally as a weighted multi-counter system, where for each program variable we introduce one such symbol here. So here in this case, since we only have one symbol, this is this model is a univariate distribution. And every time we take a transition with a corresponding symbol, we increment the counter by 1. We do not allow any decrementation, only increments by 1. And at the end, if we reach a final state, then we basically see what is the value of the counter. This corresponds to the program variable's valuation, and the coefficient, so the multiplication of all the weights, corresponds to the probability that the state occurs. So here we can see the probability distribution that is encoded by this automaton here. It's just a geometric distribution, and since the slide is for finite space, I can't display the whole distribution, but this goes on for infinity. So this is an infinite support distribution. And let me just walk you through one case here. Right, this x-axis encodes, or x-axis indicates the values of the program variable associated with x, and the y-axis the probability of the state occurring. So here, for instance, we have x as the value of 0. This corresponds to this run here, right? We start, and then we directly terminate. We do not take any x transitions, therefore x is never incremented and stays at 0. And we have the coefficient of 1/2, so here we have 50%. OK, what can we now do with these weighted automata? Well, we can now apply a very basic operation, such as we can add another automaton to the end of it. Here, in this case, we add another x transition, and this results in a shift on our distribution, right? So we basically increment by 1. What we also can do is we, for instance, and this is very important, we can weight the whole automaton, so we scale down the distribution. Therefore, we can also handle subdistributions here. But now I want to talk about the semantics, and therefore I will switch the topic really quick, and I will talk about fish. Some of you might be familiar with the goldfish piranha problem. If you're not, I will briefly introduce it. So we have two protagonists. We have the goldfish and we have the piranha. And we also have our location, namely the fishbowl. but since we are dealing with probabilities and uncertainty here, we paint this fishbowl black so we cannot see anything. Now, at the start of this problem, we have our fishbowl. Remember, we painted it black for some reason, so we cannot see anything, but we know that there's one fish inside. And we know that it is either a goldfish with probability 1/2 or a piranha with probability 1/2. Now what we do is we throw another piranha inside, and right before any of the fish may attack each other, we just remove one fish, and this happens to be a piranha. Now, the question here is, what is the probability that we start with a piranha given that we remove one at the end after following all these steps? And yeah, since this is my talk, I want to apply our automata-theoretic construction in order to resolve this question. Okay, so for this, we first need to model this as a probabilistic program, a very simple one. Here we have two variables p and r, and the values are 0 and 1, where 0 stands for goldfish and 1 stands for piranha. So here we flip a coin, and based on the outcome, p is either 0, so there's a goldfish inside, or 1, so there's a piranha inside. If p is equal to 1, so if there's a piranha inside, then we throw another piranha in, and we remove one fish directly, so therefore we remove a piranha with probability 1. And in the other case, we just throw a coin again. And at the end, we observe that we have removed a piranha in fact. So what we also assume is that all variables have the value of 0 initially. Now, I want to show you how these semantics work. On the left-hand side, we can see the program. On the right-hand side, the current automaton. Here, this is the automaton which represents our assumption, namely that every variable has the value of 0 initially. OK, let's start. First, we sample p from the Bernoulli distribution. And we have defined some distributions which can be used in our inference. For instance, here, this is how the automaton for the Bernoulli distribution looks like. Let's walk through it real quick. We have two paths here, right? This one, we don't take any p transitions. Therefore, p has the value of 0. And the weight is 1/2, so the probability is 1/2. And this path here, we take one p transition. The probability is the same. So we have 50% p 0, 50% p is 1. OK, what you would expect. Now, the next part is a bit more interesting. Here, we want to filter based on the value of p. And we want to basically split the automaton into two. One where every path satisfies this guard, namely we take exactly one p transition, and one where no path in the automaton satisfies this guard, so there's no path which has exactly one p transition. Here, since we only have two, it is very simple. We split it up into two, and now we have two separate automata on which we apply the semantics for the then branch here or the else branch respectively. So for this case, we set r to 1. Remember, we just, since our multi-counter the multi-counter system part, we just add another r transition here to the end. So we set r to 1. And then we're done with this case. And for the second case, we already seen how this geometric distribution, the Bernoulli distribution automaton looks like. So we also just append it to the end. Now we connect it to one automaton again. We are done with this if statement. And now we can briefly check whether it makes sense. So here, in this case, we have with probability 50% a piranha originally inside, and then we remove a piranha certainly. And here, at the start, we have a goldfish inside, and then with 1/2 times 1/2, so 25%, we remove a goldfish, and 1/2 times 1/2, so 25%, we remove a piranha. OK. Now at the end, we observe that we have removed a piranha. Therefore, we now want to remove every path where we do not take exactly one r transition. And here in this case, this is only this path here, right? And therefore, what we do is we remove this final state at the bottom. OK, now we are almost done. However, what we now have is the unnormalized posterior distribution. So we have a subdistribution since we have removed probability mass. And now we want to normalize this again. So therefore, we compute the probability mass of this automaton. We've shown in our publication that this is possible in polynomial time. And then we normalize or weight the whole automaton by the reciprocal of this. And now we're done. We have the normalized posterior distribution, which has a probability mass of 1 again. And we can answer our question. So what is the probability that we start with a piranha, given that we remove one at the end? And if we remember our encoding, here we have p is equal to 1, right? And on this path, so this is the path that represents that we start with a piranha, we just have to calculate the probability mass here. So we have to multiply 4/3 times 1/2, and this is equal to 2/3, which is the answer to this problem. OK, I want to summarize. What we have done is we have provided a sound framework for exact inference using these weighted automata and the basic automata-theoretic operations. What is for future work? We want to relax some syntactic restrictions. So for instance, on the expressivity of the guards that we use. We also want to use more expressive automata models, such as push-down automata or their variants, to also model more complex distributions or more complex guards. And lastly, we want to add tool support so we can infer all these rules automatically. So if you're interested, here is the paper to this brief talk, and right here is my poster. So if you're interested, you can find me at the poster session or just in the break after this talk. And I thank you very much for your attention.
Thank you. Do we have any questions?
Thanks for the talk. I was wondering if you can characterize the kinds of distributions that these automata can express.
Yeah, that's a very good question. So what we haven't done yet is that we characterize exactly the set of PGA, also the automaton called PGA. So the kinds of distributions that this automaton can actually represent. So this is something that we left for future work.
Okay.
Okay, well, let's thank the speaker again.